his collaborators. And if you're interested in the differences, you can ask me about those afterwards. So this talk is going to be about, can everyone hear me at the back? Is that, yeah? Okay, great. So this talk is about shadow tomography. Oh, not really. Oh, no. Uh-oh. I saw a thumbs up and thought it was universal. But let me try to, how about now? Is that better? Not better?
Maybe that one's only for the Zoom. See if,
okay.
Is that better?
Okay, thank you. So this talk is about shadow tomography, which is about learning properties from many copies of a quantum state, like in the lab. And this notion has a fancy name, but it's really very simple. It was introduced by Scott Aronson in 2018. We have a known set of observables that we start with, like let's call that set S. So S is a set of Hermitian operators. And we're given copies of an unknown quantum state, and we want to estimate the expected values of all the observables in that set to within a given precision epsilon. So that's the goal. And so in pictures, we have the copies of our state that come in. Oh, we have a fancy thing here. So the copies of our state come in here. I'm using M for the number of copies. In general, the state can be mixed. We also have to give our protocol the precision, the epsilon. And remember that S is fixed beforehand, but we're going to have our shadow tomography protocol, and it takes these inputs, and it's supposed to output estimates, which are numbers for every observable in S, and each of those numbers, all at once, they all have to be within epsilon of the true value. Okay, that's the goal. And you might, you might ask several questions about the setup, but one of the most natural questions is, how many copies of the state do you need to prepare to learn all of these properties of your system? And the very most naive thing you might do would have this scaling of the number of copies with the size of the set S and the precision epsilon. So let me walk you through this, this kind of scaling, which is the naive thing that you would do. So this epsilon to the -2, that's just because if you have a single observable, a single Hermitian operator, and you want to learn its expected value within epsilon, you can just take a copy, measure that observable, and repeat 1 over epsilon squared times. That's just for one observable. Okay, but now you don't just have one observable, you have S observables. So then we have this overhead that's linear in the number of observables. And then we have this extra factor of log S, and that log S factor, which you can for the most part ignore, it just comes from the fact that we want all the observables all at once to be within the epsilon interval. It's not enough for each one to be within that interval with 90% probability independently. We want all of them at once to be within that interval. Okay? This is the naive algorithm. But the interesting thing, which was shown by Aronson, is that in general, you can do exponentially better than this. So in fact, this linear scaling with the size of S is unnecessary. It's possible to have algorithms which scale as polynomials in the log of the size of the set of observables S. Now, how can you understand that? Well, you should, we're going to talk more about those types of protocols in this talk, but as a simple first case, you might think about the case where all the observables commute. So if all the observables commute, then you can just think you're kind of sampling from a probability distribution over the measured eigenvalues. And how many samples do you need? Well, in general, if you're just taking samples from a probability distribution and you have a set of random variables and you want to compute all the expected values, you can do all of them from the same reasonably small set of samples. So in the case where things commute, you kind of already know, or you could figure out in 5 minutes, that you don't need this linear factor in S. And so the interesting thing is, of course, getting that kind of scaling in the setting where the observables don't commute. Okay, and we are going to, for this talk, not talk more about kind of general sets of observables S. We're going to focus on the case where we have n qubits, and S is always a subset of the n qubit Pauli operators. Okay, so for the rest of the talk, we're going to restrict to that case, and that starts on the next slide. Are there any questions about the setup? Yes.
How are you making copies of an unknown quantum state?
Well, so you have say a quantum computer and you run the same procedure m times in parallel. I understand that there is some kind of idealization of maybe, that things are the same every time, but we're going to work with that. Well, okay, so somebody else, let's say somebody else does that. Okay. Yeah. Okay. All right. Good? All right. So I want to tell you about this, as a starting point, I want to tell you about this beautiful protocol by Huang, Kung, and Preskill from 2021, which targets this special case of Pauli observables. So again, this is my notation for the n-qubit Pauli operators. They're strings of identity x, y, and z. Each string has length n. And so we have some subset of the Pauli operators. And this protocol has two steps. In the first step remarkably can do the following thing. And I'm going to explain this in a second, but it should not be like obvious that this is possible. So I claim that in the first step of this protocol, you're going to learn all the magnitudes all at once with very few samples. You notice there's no linear scaling in the size of S here. Okay, so it's epsilon to the minus 4, which is a bit funny, but okay, times this log factor, which I told you to ignore. And we're going to learn all the absolute values up to epsilon r all at once. Okay, so that's kind of amazing that you can do that. And why is it that you can do that? Well, it's because even though the Pauli operators don't commute with one another, like many of them, you know what I mean. Some of them commute, but some don't. If you take p tensor p and let p range over all Pauli operators, these 4 to the n operators all commute with one another. So if I take 2 copies of my state rho and take the expected value of p tensor p, I get trace of rho p squared. And since these all commute, I can kind of do them all at once with this very low cost. Okay. So, and for the experts, this uses only 2-copy Clifford measurements, meaning I'm only entangling 2 copies at a time. Prepare 2 copies, and I measure in the basis that diagonalizes all these operators. And I do that this many times, and I get to learn all these magnitudes of the things I care about. And then if I know all the magnitudes to epsilon r, then there's a little bit more I can do before I go to the second step. And this little bit more is important. From this data, we already know that some of the, we can already identify any Pauli operator that doesn't have a strong signal. You see, we only care about the expected value up to epsilon r. So if I do this and I find that the magnitude has epsilon over 10, then I actually don't need to learn its sign. I can just set my estimate to 0, and I'm within epsilon. I know that I'll be within epsilon. If it's plus epsilon of 10, minus epsilon of 10, it doesn't matter. So in this first step, I get to throw away a lot of the Paulis in the sense that I don't need to care about them, their signs going forward. There's going to be some where the signal is large, where the magnitude of the expected value is at least epsilon. Those ones I need to figure out what the sign is going forward. But the rest of them, I can just set my estimate to 0. Make sense? Okay, so in the second stage, and this I'm not going to explain because we're not going to build on this in any way, there's a kind of, again, a very beautiful protocol called the gentle majority vote that learns the signs of the Paulis for which you have a strong signal, okay? And the important thing for us in this talk is that for this step, you need to do a measurement on epsilon to the minus 2 log s copies at a time. And this is a log that I don't want you to ignore, okay? This, and let me talk about that in a second. So I claim this protocol is almost the best we could hope for shadow tomography for Pauli observables. And again, I'm going to explain that on the next slide. The sample complexity, meaning this is what I started with asking about, the number of copies, that's really good. It's epsilon to the minus 4 log s. There's no linear factor in the number of observables. That's excellent. The runtime is also good. Everything is efficient in terms, like it's polynomial in the number of qubits, the inverse error, and the number of observables. You know, the runtime can't be less than linear in the number of observables because you have to output all the observables, expected values. So that's good. The number of copies per measurement, as we said, there's this second stage that I didn't really talk about where you have to do this entangling measurement on log s copies, or epsilon to the minus 2 log s copies at a time. And that's the thing that that's the reason why I said almost as good as we could hope for, because if you have, like, say someone hands you m copies of a quantum state, it's going to be a lot easier if I can just measure one at a time. Like, say my quantum computer can only, I have a memory that can hold those m copies, or maybe they're handed to me one at a time, then I can just measure them individually. But if I have to take epsilon to the minus 2 log s of them and do some entangling measurement, then I'm doing a much bigger quantum computation that scales now with the number of observables that I care about. And so that's the thing that we would like to improve. Can we get away with fewer copies per measurement? Okay, make sense? Okay. So we define this thing that we call triply efficient shallow tomography, where we just aim for that. Okay, so we want to keep our number of copies or number of samples, same thing, to be scaling polylogarithmically in the size of s and 1 over epsilon. We want to have a good efficient runtime, just like in the protocol you just saw. But now we only want to have algorithms or protocols that make measurements on a constant number of copies at a time. And in this talk, it's always going to be 1 or 2. Okay, so only 1 or 2. All right, that's what we call triply efficient shadow tomography. And you might ask, like, is this possible at all, right? And we know or knew before our work that it could be achieved in certain special cases. So let me tell you about one of those that many of you probably are already aware of. Okay, again, this was all worked out in several papers that came out around the same time and is often attributed to Huang, Kung, and Preskill. It's a special case of this classical shadows procedure that they pioneered. So here we're talking about a specific set of Pauli operators for which this is going to be triply efficient. And the specific set is the Pauli operators where the total weight is a constant k. So the weight means the number of non-identity terms in this tensor product. Okay, so these are local operators. So it's like you could have x tensor I, that's a 2 local operator. Okay, and now we're going to take the weight, the locality, to be a constant independent of n. So if I take weight k operators, the number of them is, well, anyways, yeah, you can do the combinatorics, but we're taking k to be constant. That's important. And so here's the protocol from the classical shadows paper and these other papers. You just measure each qubit of the unknown state in a uniformly random measurement basis x, y, or z. Okay, and then you do this for one copy of the state, and then you do it again for another copy. So you're only doing one copy at a time. Okay, so let me take you through that. Here's our state rho, say it has 6 qubits. I choose a random basis for this qubit. Maybe it's x, maybe y for that one, x. I choose just a random basis for each qubit. Now I'm going to ask you a question. I answered the question, sorry. You might ask, what is the probability that a fixed k local Pauli is diagonal in the basis that I just chose? Okay, so for it to be diagonal in that basis that I just chose, it has to be, there's k places where the Pauli is not the identity, and it has to line up with these bases at each of those k places. Okay, so that probability is 1 over 3 to the k, right? And for that reason, every time you do one of these random measurements, 1 over 3 to the k fraction of all of these Paulis, you get like a signal for. Okay, so the number of samples that you need is roughly 3 to the k. Okay, it's 3 to the k times epsilon minus 2 log s. Again, you ignore this log s. Okay, so this 3 to the k is the same as that 3 to the k. But what's good about this is that we only made single copy measurements. The number of copies we need is remember, k is a constant, so this is polynomial in 1 over epsilon and log s, just like we wanted, and it's also time efficient. So this is a triply efficient protocol for local Pauli observables. Okay, that's a very nice protocol. Now, yeah, so now I want to take us on a slight detour. It's not really a detour. I want to understand protocols like this in terms of graph coloring. And, this is a pretty normal thing to do, but we're going to add a slight twist at the end. Okay, so let's think about if we have a set of Pauli observables, we are going to think about the commutation graph, which is a graph that has a vertex for each observable in the set. And oh, there's this little thing that's in the way, isn't there? Let me move that. Okay. And an edge between any two pallies that don't commute. Okay, so this is the commutation graph. Oh no, we stopped advancing because I clicked on that weird thing. Oh, there we go. Okay, so here's an example. So we have 6 pallies, and I just drew all the pallies, and then I put an edge like between XX and IY because those two don't commute, etc. Okay, so that's the commutation graph. Now, shadow tomography protocols like the one we just saw that are based on single copy Clifford measurements are associated with colorings of this graph. So let's see how that works. So a coloring of a graph, by the way, is I take some number of colors. In this case, there's 4 colors, and I have to color each vertex. I color each vertex, and the vertices that are adjacent have to be colored with different colors. Okay, and when you do that, like in this example, this is a coloring of this graph with 4 colors. Just because of the rules of coloring and the way the graph is constructed, whenever you have an edge, you have different colors. So the vertices that are all of one color, like these purple vertices, they all commute with one another. So a coloring of this graph with, say, chi colors is a deterministic partition of the set of polyobservables into chi commuting sets, all of which can be measured with few measurements, right? So you think about, if I want to just like have a deterministic schedule of measurements that learns all the polys, well, I can get that from a coloring, okay? And of course, because it's polys and commuting polys, in fact, each measurement is Clifford. But this actually doesn't quite capture protocols like the one we just saw, like the classical shadows protocol. So now I have to give a little twist on this. And for that, you have to go, well, I have to introduce this definition from graph theory, although it's not really important for the rest of the talk, but we will be talking about fractional coloring. So you don't need to retain the definition, but you need to know that it exists, okay? Because I'm going to say the word fractional coloring. So fractional coloring is a linear programming relaxation of a coloring. It's well known in graph theory. It is a probability distribution over independent sets of the graph, such that if I fix a vertex of the graph, in this case a pally, the probability that it's in an independent set drawn from that distribution is lower bounded by 1 over chi. This is a coloring with chi colors. But here, because it's a fractional coloring, chi does not need to be an integer. Okay, so this is a kind of relaxation of the notion of a coloring. And this is exactly the thing that describes randomized schedules of Clifford measurements that are capable of learning all of these pallies with single copy Clifford measurements. Just like the classical shadows protocol. Okay, so that defines a fractional coloring. And yeah, you can ask me more about this afterwards if you have questions. Okay, so just to summarize this first part, for k-local polyobservables, we saw there is already this triply efficient shadow tomography algorithm. It's sample efficient, it's time efficient, it only uses single copy Clifford measurements, and it learns all of these things. And we can also rephrase it in terms of fractional colorings if we like. And in this work, we want to give triply efficient protocols for other sets of polyobservables. And so what sets are we interested in? Well, so we give a triply efficient protocol for k-body fermionic operators. So these are operators that appear, for example, in quantum chemistry. Those would describe like two-body interactions between fermionic particles, or k-body interactions between fermionic particles for any constant k. Just like the k-local poly operators can be thought of as like k-local interactions between spins. Now we think about k-body fermionic interactions. It's a different set of observables. And we also give a triply efficient scheme for the set of all poly operators. I want to just call out that the triply efficient scheme for the set of all poly operators does not give a triply efficient scheme for some subset like this one, because the runtime is allowed to be polynomial in the size of the set. So this scheme is allowed to have a runtime that's polynomial in 4 to the n, and that's because you have to output all 4 to the n observables expected values at the end of it anyways. Whereas this one is much more constrained in its runtime, okay? Now, what's interesting about these observables is that for these ones, it's actually impossible to achieve sample efficiency, the thing that we got for k-local poly observables, using just single copy measurements, okay? That's not possible. In fact, like for all Pauli operators, for example, any protocol that uses just single copy measurements of any kind, even adaptively, requires on the order of 2 to the n measurements. And this was proven by Chen, Kotler, Huang, and Li. And by combining techniques from their paper and this paper by Hastings O'Donnell with some other stuff from math, you can also prove similar lower bounds for the K-body fermionic operators. I say similar in the sense that they rule out sample efficient protocols. In that case, they're not exponential time lower bounds or exponential lower bounds, but they rule out sample efficient single copy protocols. Okay, so for these observables, we actually require at least 2 copy measurements, and measurements that entangle 2 copies or more at a time in order to achieve our goals. And that's what we do. Are there any questions at this point? Yes. No, that's the tricky thing. It's like even in the case, like, okay, so yeah, I mean, certainly once you've decided to use a graph coloring strategy, even if you're in a case where the graph could be colored with few colors, it can be very hard to find good colorings. Yeah, there's no doubt about that. So I have not given any details about how our protocols work, but now I'm going to do that. Okay. Other questions? Okay. Right. So let me give you this kind of framework that we work within. So we're going to take our subset of Pauli observables, and we're going to use a variant of this Huang-Kuhn-Preskill protocol, which was proposed as a heuristic. But again, so in this variant, they said, well, maybe you could use this in practice if you had a good coloring algorithm. And in our work, we're going to show how you can get these good coloring algorithms. Okay, but let me show you how the protocol works. So we're going to, again, just like the protocol I showed you at the beginning, we're going to use these Bell measurements, the measurements that in the basis that diagonalizes P tensor P for all Pauli's P. And we're going to use that to learn the set of all the Paulis that have a non-trivial signal, so that the expected value is at least epsilon in magnitude. And then we're going to throw away or output 0 as our estimate of all the ones that are not in that set, because we know that's within epsilon of the value. So that's the same first step as this protocol I showed you at the beginning. And then in the second step, instead of this fancy gentle measurement thing, we're just going to find in some way a single copy Clifford measurement protocol that learns all the Paulis, the expected values for Paulis, but only in this set. So the purpose of this first step is to winnow down from S to this set S epsilon, which is only the Paulis that have a non-trivial signal. And now we have to, your question is very relevant here because I haven't told you at all how we're going to do this step 2. And if I don't tell you that, then it's sort of this heuristic algorithm. But it's important to, if you like, in order to turn that into like a provable protocol with a performance guarantee, we need to show you how to do this and show that it can be done. Okay. So as an example, like we had maybe we have this set of 6 Paulis, and we have our copies of rho and our epsilon. And in step 1, we take those as input, and we do these 2 copy measurements in this fancy Clifford basis that diagonalizes P tensor P. And that's going to winnow down our set to this S epsilon, which depends on the unknown state rho in some way that's very hard to understand, analytically at least. And now we just need to learn the expected values for these observables. But then how is it, like, is it actually easier in the worst case? I mean, it's kind of surprising, but it actually is. So in graphs, we start with the commutation graph of this big set S, and then we do this step 1, and then it winnows down to some graph with fewer edges and fewer vertices. And the step 2, where we have to learn using single copy Clifford measurements, that amounts to computing a fractional coloring or fractional coloring of this graph with a small size. Okay, so that's our goal in step 2. And okay, so if we can find a good fractional coloring here with small size chi, then the sample complexity is good too. I mean, it's epsilon minus 4. That comes from this first step with the 2 copy Bell measurements. And then we get a linear scaling in chi 1 over epsilon squared, and this log factor that we said we would not worry about. As a small aside, because all the measurements in this protocol are Clifford, this protocol can also be viewed as learning a classical compressed representation of rho, which consists of all the measurement bases and measurement outcomes that were used in the protocol. And that's because the Clifford formalism is completely classically simulable. So I will talk a little bit more about this aside later, but for now, we can move on. Okay, so this framework, as Priya asked, this framework is only useful if we can compute good fractional colorings of this commutation graph after we've winnowed it down, right? And it has to be that that winnowed down graph can be colored with vastly fewer colors than is even possible for the larger graph, because we said that larger graph does not admit good single copy measurement protocols. For the case of all Pallies, for example, the number of colors required would be exponential in n for this graph. But now we want to color this with a polynomial in n number of colors. Okay? So how can we do this? Okay, so I claim we know one useful property of this winnowed down graph. Remember, this graph depends in some funny way on the unknown state. But we do know one useful property. What is that useful property? Okay, so I have to tell you what a clique is. A clique is a fully connected subgraph. Like a triangle is a clique of size 3. An edge is a clique of size 2. A clique of size 4 is like a square with an X in the middle. Okay. So the largest clique in this graph, I claim has size at most 1 over epsilon squared, which is interesting because this graph could have like exponentially many vertices, right? Whereas this largest clique, its size is not going with n. Okay. So that's one property we know about this graph. The other thing that you might, before I tell you how this is proven, cliques are obstructions to coloring, right? If I have a clique like of size k, that means I need at least k colors, because every vertex in the clique needs to be a different color. Okay, so cliques are obstructions to coloring. So this kind of seems like good news, right? Okay, so the proof is really like one line, and I'm not actually going to go through it, but it's here, okay? And it sort of comes from an uncertainty principle when you have anti-commuting Paulis. You see, because a clique in this graph is a set of pairwise anti-commuting Paulis. And you can get a kind of uncertainty principle that constrains the sum of the squares of the expected values of such a set. And that leads directly to, like this equation can be rearranged to t is at most 1 over epsilon squared, and t is the size of the clique. But okay, so I said that a clique is an obstruction to coloring. So it seems like good news, but unfortunately, it's not the only obstruction to coloring. So there are graphs where the largest clique is of size 2. There's no triangles. But the number of colors needed to color that graph is like square root the number of vertices, and the number, you can have families of graphs where the number of vertices grow, and then the number of colors needed to color these graphs are unbounded. They grow like the square root of the number of vertices, but there's no triangles in the graph. So cliques are not the only obstruction to coloring, unfortunately. So on its own, this little lemma does not let us color the graph right away, or fractionally color it for that matter. We do have one additional property that we know about this graph, which is almost completely kind of silly to even say, which is that it comes from this bigger graph by removing vertices and edges that touch them, right? We started with a set of observables, and we removed the ones that didn't have a good signal. And then all the edges that touch those vertices also get removed. So in graph theory language, we would say this is an induced subgraph of this larger graph G of S. And this graph we kind of understand because we know what all the observables are. This one we don't understand because we don't even know what the vertices are. Okay, so we know these two properties, that we have an induced subgraph of this larger graph. Am I out of time? 5 minutes, perfect. Okay, which I'm not sure it's perfect, but we'll work with it. Okay, so we know these two properties. And so our goal is to show that any graph, which is an induced subgraph of this larger graph, is chi, in graph theory, you call this chi bounded, that there is an upper bound on the number of colors you need as a function of the size of the largest clique. General graphs don't have that upper bound. There's no upper bound on chromatic number, the number of colors, as a function of the size of the largest clique. But that it can be true for certain families of graphs, and we hope that it's true for the family of induced subgraphs of this graph that we care about. And why? Let me give you an example of a chi-bounded family, okay, that has this property, all right? So, sorry, this is the last graph theory thing that I'm going to hope to define here. If I have like a path in a graph, like a line of vertices where everyone's connected to the one before it, it's called an induced path if it contains all the edges of the larger graph that have both endpoints in the path. Okay, so like here, this green set of edges and vertices, that's an induced path because every edge in the larger graph that touches one of these vertices is also contained in the path. Okay, so that's called an induced path. Like if there was an edge between this vertex and that vertex, like a blue edge, then this green path would not be an induced path. Okay, that's an induced path. And Giarfas, who's a mathematician, showed that if you have the family of all graphs where the longest induced path has length L, so you don't have induced paths that are too long, then you can always color such a graph with L to the omega minus 1 colors, where omega is the size of the largest clique. So this is an example of a chi-bounded family where you have an upper bound on chromatic number as a function of the clique number. Okay, the family of all graphs with no long induced paths. Longest induced path has size length L. And you might say, okay, that sounds nothing like what you were talking about before. But, oh, and the coloring can also be computed efficiently in this case. But actually, it turns out not to be so irrelevant because now this is not how we get, this is not really how we get our protocols, but you can get a protocol by this argument, and I want to show you how it works because I think it's instructive. Like if we take the graph that contains all the Paulis, okay, so this is a graph with 4 to the n vertices. In fact, that graph does not have long induced paths. That's a graph with 4 to the n vertices, but the longest induced path in that graph is just 2n plus 1. Okay, so that's like logarithmic in the number of vertices. And you can show this kind of algebraically because if you had, basically, if you had a set of vertices that form an induced path of length L, then from them you can construct these products of the neighboring vertices up to 1, 2, 3, 4, etc. So you get L different products, and these are all pairwise anti-commuting. And in a Hilbert space of n qubits, you can't have more than 2n plus 1 pairwise anti-commuting operators. This is a fact from algebra. Okay, so that's kind of the proof of this statement. But the fact that these, so let me show you how you get a protocol from this. Okay, so the longest induced path in these commutation graphs is not too long. It's at most 2n plus 1. So from Giarfas's theorem, which says that that family is chi-bounded, we get that any induced subgraph of this graph that has largest clique of size omega can be colored with at most n to the order omega colors. And that gives a shadow tomography protocol when we apply it to the induced subgraph we care about, where we know that the largest clique has size 1 over epsilon squared. And you know, this protocol has sample complexity n to the 1 over omega 1 over epsilon squared, which is actually not the best we can do for the set of all Paulis, but I wanted to illustrate kind of how these topics of chi-boundedness and tomography connect with one another. And I also wanted to give this example because it has an interesting consequence that we do not get from our other protocol. And so I want to tell you about that consequence very briefly, and then I will wrap up because I think I'm within a minute maybe or two. 1? 0, okay. So it has the following interesting consequence, which if you were sleeping, you might still find interesting. Okay, so let's say I want to transmit to you the expected values of all the Pauli observables in a quantum state that you don't know. Okay, how many bits do I need to do that? Okay, how many bits do I have to send you? And I'm gonna allow myself to only transmit them to a constant error epsilon. So epsilon is like a very small constant, like 1/1000th or 1/1,000,000th. So from this shadow tomography protocol, you can infer that there exists a classical compressed representation that is of polynomial size. And I can send that to you. And then given any n-qubit Pauli operator and this polynomial size classical data, you can efficiently extract, meaning polynomial time, the expected value of any paleobservable up to that epsilon constant error in this case. So that's a funny thing, that you have this compressed representation of polynomial size with efficient retrieval for all paleobservables. It was not previously known to exist. Okay, and then we do a similar thing. I talked about all pallies, but we do a similar thing for K-body fermionic observables. This is technically more complicated. It improves exponentially over previous protocols that were based on single copy measurements. And so this is the bottom line of my talk, and I'm ending here. We saw that a fractional coloring is associated with shadow tomography protocols with one copy Clifford measurements. But this other notion of chi-boundedness for the family of induced subgraphs of this commutation graph is associated with shadow tomography protocol with two copy Clifford measurements. And we use such protocols to get, well, new protocols for K-body fermionic observables and a set of all paleobservables. Okay, thanks.